All right, so number one is just find the area. The area ones are, they're simpler problems, but they're a little tricky because it doesn't tell you if it's dx or dy. You kind of just have to look at it and see, do you have an upper graph and a lower graph, or do you have a right graph and a left graph? All right, to find the area enclosed by these graphs, y equals negative x squared. So that is a regular old parabola that is just upside down. So all the points you normally get, or just reflecting them. So instead of like 1, 1, it's 1, -1, and 2, -4, and 3, -9. Right, so an upside down parabola. And then we have y equals square root of x. So 0, 0, 1, 1, 4, 2. This will be our square root graph. And then the vertical line, x equals 3. So here, oh, whoops, I put that point there. Sorry, that's good. 4, 2. And then we've got the vertical line, x equals 3. And so this is the area, it looks like a shark tooth or something here. This is the area that we are finding. So this is going to be a dx problem. We have an upper graph and a lower graph. The square root graph is above the parabola all the time, right? So this is going to be dx. We're going to integrate from 0 to 3. And it's upper graph minus lower graph. So that's the square root of x minus the parabola. Now it's going to be minus negative, so it'll be plus x squared dx. Now, like the one we just went over in the homework, you're going to want to write this as x to the 1/2 and then go and work that out. And again, I'll come back and work them all out if we have time. I just want to get through the setup for all of them at least. All right, number 2, find the area enclosed by these graphs and the x-axis. All right, so let's go ahead and plug in some numbers here. I usually just start with 0. If we plug in 0 for x, we're going to get 1. If we plug in 1 for x, we'll have -1 plus 1, that's going to be 0. And we can't go any further that direction, because if we plug in 2, we're going to have a square root of -1. So I'm going to need to go the opposite direction. So let me find a number over here that I could plug in that's going to actually work out nicely. Let's do -3. If we do -3, the negatives will cancel. We'll have 3 plus 1, which is 4. And then square root of 4 is 2. So we'll have -3, 2. And I think that's all that's going to fit on this graph. So something like that. All right, and then y equals x plus 5. So that's linear. It's going to start at 5 and have a slope of 1. And then the x-axis. So this is the area that we're finding. And this is going to be a dy problem. It is sideways. You don't have one graph that's above the other all the time. They kind of meet right here. There's an intersection and it splits. But if you turn it on its side, now this curve is above the line all the time. So it's going to be a right graph minus left graph. And if it helps you to put in an R and an L to see which one's which, then just do that. So the curve is the right one, the line is the left one. Now, since we've decided it's dy, we immediately have to stop what we're doing and go and rearrange these equations. Let's do that. We're going to square both sides. And then subtract the 1. And then we're going to divide through by a negative. So everything is just going to flip its sign. So it'll be -y squared plus 1 equals x. So that's our first equation. This one's a little easier. All we have to do is subtract 5. But you're going to get points for doing that on your test, rearranging those, because you have to do that in order to set this up. So I'm going to ask you guys the boundaries. It's going to be a dy problem. So hey guys, look at the y-axis. What are going to be the boundaries on our integral? Good, nice job guys. So 0 to 2, perfect. And it's right graph minus left graph. So it's going to be this negative y squared plus 1 minus y minus 5 dy. So again, these are y values for the boundaries. Everything in here says y, and then we have a dy. If you mix and match the x's and y's, that's like a big whoops. All right, so you're going to need to distribute the negative, combine like terms, then do your antiderivative. Again, I'll come back and work that out if we have time. I just want to make sure I get to set them all up because I think you guys could finish that okay. I just want to make sure that you can set them up. All right, find the volume of the solid. So now we're done with areas. Now we're moving into the volumes. The base is bounded by these graphs, and then we have rectangles popping up out of the paper at us, and the height is 4 times the base, perpendicular to the x-axis. So these ones come right out and tell you if it's dx or dy. So this is going to be a dx problem. All right, so first graph, y equals x squared minus 2. So a parabola that is moved down 2. So it's all your regular points on a parabola just moved down 2 units. The whole thing just gets scooted down. All right, and then y equals negative x. So that's going to go through the origin and have a slope of negative 1. So this is the base of this 3-dimensional object. And you have to imagine these rectangles popping up out of the paper at you. So I'm going to draw a rectangle. Again, it's like you have an infinite like sliced loaf of bread, and I'm just taking one of the slices out. So the base of this rectangle is going to be upper graph minus lower graph. And so the upper graph is the line that was negative x minus the lower graph is this parabola x squared minus 2. So upper graph minus lower graph, and I'm just going to distribute the negative to clean that up a little bit. It'll be negative x minus x squared plus 2. So when we set up the integral, it's going to be dx. So I'm looking at my x-axis for my boundaries. It's where these intersections are. So that's going to be from negative 2 to positive 1. And inside of there, you're going to put the area of your shape. So it's going to be base times height. This is the base. And then the height is 4 times that. So the height is going to be 4 times this exact same thing. So it would be 4 times this times this. So it's 4 times that stuff squared. And I would let you just put that one in the calculator. All right, so I wouldn't make, oh, sorry, I forgot the squared. Because you would have to multiply this times itself, and that would just be an awful lot. If it's only 2 terms, I'm going to make you work it out. But if it's 3, you can just type that in the calculator. All right, number 4, find the volume of the solid whose base is bounded by these graphs, square cross sections, perpendicular to the y-axis. All right, so let's graph these, but then the very next thing I'm going to do is I'm going to rearrange the equations, because if it's going to be a dy problem, I need to fix these so that they're the other way around. All right, so this is a line. It's going to start at positive 3, so point at 0, 3. Slope is negative 1/3, so we're going to go down 1 over 3. All right, and then here, this is going to be a square root graph, also moved up 3. So you're going to start again at 0, 3, and then let me try and plug in some other numbers. If we plug in 1, we're going to have negative 1 plus 3, which would be 2. So 1, 2. If I plug in 4, I'm just going to go to all the perfect squares. If I plug in 4, I'll have negative 2 plus 3, which would be 1. So 4, 1. And if you plug in 9, you'll have negative 3 plus 3, which would be 0. So that's where they're going to intersect. And so this area is the base of this 3-dimensional object. And again, it's going to be a dy problem. So our cross sections are going this way. And so the base of our shape is going to be right graph minus left graph. But I do need to rearrange these. So let's go ahead and do that. You can't be scared of the algebra. We're just gonna have to get x by itself. So subtract over the 3. So y minus 3 equals -1/3 x. And then you're gonna multiply by a -3 to cancel out the -1/3. So I'm gonna just multiply everything by a -3 here to cancel that out. That'll be -3y plus 9 equals x. So there's that equation. We're going to do the same thing for this one. So subtract over the 3. And then we're going to divide through by a negative. So everything is just going to flip-flop its sign. It'll be -y plus 3 equals square root of x. And then we're going to square both sides. And actually, let's go ahead and just multiply that out right now. Since, well, yeah, let's just go ahead and multiply it out right now. It would be -y plus 3 times -y plus 3. We may as well just go ahead and do that. So that would be y squared. Outsides would give you -3y. Insides would give you -3y. So that's -6y. And then 3 times 3 would be 9. All right, so setting this up, we're going to need to use y values for our boundaries. So look at your y-axis. This one's going to be from 0 to 3. And what was the shape? Forgot at this point. Squares. So I'm going to draw my square off to the side. It's going to need to be kind of small because I sort of ran out of room here. So the base of that square matches up with right graph minus left graph. Again, put the R and the L in there if that helps you. Right graph minus left graph. The right graph is the line, so that's this one, the -3y plus 9. And then minus the left graph, which is this one. All right, and so what we're going to put in here is the area of our shape. And you know what, actually, I probably didn't need to multiply that out because I'm not going to make you guys do this one by hand anyway. What's going to go in here is the area of the square, which is all of that squared. Well, I don't know. Let me see how difficult this is going to be. We would need to distribute this negative sign. So I distributed the negative through there. Actually, does some of that cancel? Yeah, you know what? We can do this by hand because some of this is going to cancel, so it actually won't even be too bad. This would be integral from 0 to 3. The 9s are going to cancel. We'll have -y squared and then plus 3y squared dy. Yeah, you could multiply that out and then do an antiderivative. I think I would have you do that one by hand. Because the 9s canceled, that actually ended up not being too terrible. Again, if it's 2 terms, it's not that hard to square it. All right, number 5. The region enclosed by the x-axis, the line x equals 2, all right, that's this right here. And the curve y equals x squared. So that's just your regular parabola. So 0, 0, 1, 1, 2, 4. Those are our points on the parabola here. I'm not drawing in the rest of the parabola because I would just end up erasing it anyway. This is the shape that we're looking at. And we're going to spin that around the x-axis. So I'm going to draw my ghost shape down here. You can erase all the tails, like everything that's outside of that. And so this looks like a really wide tornado or something, like a really wide funnel, or like a really wide top that you could spin. But anyway, they're all round, so this is all going to be pi r squared. So pi r squared dx. This is just disks. There's not a hole through this one. All right, so boundaries will be x values. That'll be 0 to 2. And the radius is upper graph minus lower graph, which is just going to be x squared. It would be x squared minus nothing. And then you could work that out by hand. You would do x squared squared, that would be x to the 4th, and then do that antiderivative, upper boundary minus lower boundary. All right, number 6, we're using that same area from number 5. So I'm going to just redraw this. We had, again, this parabola 0, 0, 1, 1, 2, 4. And then the vertical line x equals 2. So that's the same shape that we just did in number 5. This time, though, we're going to spin around the line x equals 3. So here's our axis of rotation. And I'm going to draw my ghost shape on the other side. So again, this looks like a funnel, that hole in the middle. All right, so this one's going to be a dy problem. It's like we took the y-axis and scooted it over a little bit. So it's going to be a dy problem. We're going to have pi r squared minus r squared dy. And so I'm going to need to take the equation and rearrange it. So the equation was y equals x squared. And I'm going back to number 5, because again, we reused the same problem. So I'm going to square root both sides. You have square root of y equals x. So that's what we're going to be using. So the outside radius goes all the way to the edge. And then the inside radius is just this piece. So it's going to be right graph minus left graph. The right graph is the axis of rotation, so that's 3, minus the left graph is square root of y. And then for the inside radius, it's going to be 3 minus 2, which is 1. You can write 3 minus 2 there, or a lot of times people will just look at this and go, oh, that distance is just 1 unit. And then you would need y values for your boundaries. So it's going to go from 0 to 4. And you could multiply that out. I think I would let you type that in your calculator, though, because with the square root, that's going to be kind of weird. So I think I would just let you type that. All right, and then last one. Find the volume formed by rotating the region bounded by. All right, y equals x cubed. So that's going to be our wiggle graph. We're going to have 0, 0, 1, 1. And then the reflected point over here, -1, -1, and then 2, 8. And then -2, -8. All right, so that's our y equals x cubed. We have y equals 0, which is just the x-axis. And then x equals 2. So vertical line at x equals 2. So this is our shape. And I'm going to erase all the tails outside of that. So just that. And we're going to spin that around the line y equals -2. So I'm going to dot that in. Here's y equals -2. And I'm going to draw my ghost shape on the other side, like the reflection of that. So hey guys, is this one going to be dx or dy? That's actually like half the battle right there, is deciding if it's dx or dy. Which one is this going to be, guys? Yeah, good. Nice job, guys. Perfect. dx. Nice job. It's like we took the x-axis and just moved it down a bit. So dx. All right, so this is going to be, and this one has a hole in the middle. So this is going to be pi r squared minus r squared dx. We need x values for our boundaries since it's a dx problem. So look at your x-axis. It's going to be from 0 to 2. And then let me color code here. So your outside radius goes all the way to the edge. And then the inside one is just from here to here. So upper graph minus lower graph. The upper graph is x cubed. This is for the outside radius, pink one here. So the upper graph is x cubed minus the lower graph, which is -2. So it's going to be minus -2. That would be plus 2. And then the inside radius, this is the axis, that would be 0. So 0 minus -2, which would just be 2. And again, a lot of times people will just look at this and go, oh, from there to there is 2 units. So this radius would be 2, the one I've labeled blue there. All right, so we're going to have to multiply this out. If you want to write x cubed plus 2 twice off to the side, we're going to have to multiply that out. So x cubed times x cubed, that would be x to the 6. The outsides will give you 2x cubed. The insides will give you 2x cubed. So together that's 4x cubed. And then 2 times 2 is 4. But then actually you're going to have -4. So those are going to cancel. And so let me just finish this one up since we're right here. Antiderivative would be 1/7 x to the 7th plus x to the 4th, such that 0 to 2. And then you really just need to plug in 2 because the lower boundary is 0. So that's not going to, I mean, if you plug in 0 for these x's, it's just going to be 0. So that would be 1/7 times 2 to the 7th, whatever that is. And then plus 2 to the 4th is 16, but you could honestly just write 2 to the 4th if you wanted to. You don't need to simplify these because it's going to be free response. All right, I have 3 minutes. Do you guys want to pick one for me to go back and finish up? Like I'll actually finish the whole problem or show you how to type it in the calculator? All right, I'm not hearing anything, so I'm going to end the recording there.